Hello everyone. This is the second lecture, video lecture that I uploaded for this Friday. So the hydrostatic force on curved surfaces. So first thing I need to say, it's covered in chapter 2.6, and this is the second last content that we're planning to cover in the hydrostatic force. The only one content left is about buoyancy. We will cover that next Monday, and we're done with chapter 2. So about the hydrostatic force on curved surfaces. So first, it's much simpler than what we did before, but it's based on what we did before. The reason is we are use a lot of approximations here to simplify the process. It's not an accurate value, but it's a valid value for consideration. And also, you need to remember for the hydrostatic force on curved surfaces, we need to calculate the force on the horizontal direction and the force vertically differently. They are calculated separately. They are calculated separately. Then let's have a look at how we do it. So usually is okay. For example, you have a curve. If you have a here is the water, the surface of the water, and then you have a board under it. You have a board under it, and then you connect it, the end of the board, to the top of the surface. Okay, and this part is the key that we can solve for FV and FH. Let's use capitalized H here. So the basic thoughts or basic steps are disassemble plus projection. Okay, you need to divide this whole piece into different parts and then sometimes do projection. So for example, for this specific settings, you have a board and the water, we can divide the whole part shaded into two parts. Okay, this is our part 1, and the rest is our part 2. And if we put a force here is, okay, so that's F1, and this is F2. And the weight of the right part, we call it W1. And the weight from the air, we can call it weight air. And the weight on this part, we call it W2. It's not very readable, so let me change color. It's called W2. And we have FH1 here and FH2 here. And we have a vertical force work on the bottom of the board. We call it FV here. Okay, so through this disassemble, we basically can divide it into two pieces and considering 3 different weights and 5 different forces. Through free body diagram analysis, they should balance with each other. Then if we take a look at all the forces on the vertical direction, we have our FV equals weight of air plus weight 1 plus weight 2. Right, this is for vertical balance. Then for horizontal force, we think that F1 equals F2 because of because they are symmetrical, right? And at the same time, we think that FH2 equals FH1. This is based on horizontal force balance. In another word, if we summarize all the forces on the horizontal direction, we have F1 plus FH1, it equals to F2 plus FH2. And since F1 equals F2, so FH1 should equals FH2, right? And this is okay. Then if we go back to the question through this free body diagram analysis, if we go back to the question, so what is FV, which is this one, and what is the horizontal force, which is this one, suffered by the board or exert by the water on the board. It's kind of pretty straightforward that your FV equals to the weight from all above, right? Including air, W1, W2. So you need to do the connection, you need to define the body and then just calculate the weight of the body. Sometimes you don't need to consider W air because when it's very deep, theoretically you do need to consider it because the influence of atmospheric pressure can be negligible. And then next let's take a look about FH2. FH2 actually is FH. That's the horizontal force, horizontal static force exert on the board, and it equals FH1. And FH1 is if you project this board to the left hand side, it will become an equivalent. What's the shape? First, let's think about what is the shape. If we project this board to the left panel, it will become a, let me try to draw it. So what you are seeing from the front is this, but if we consider the the spatial, it's something look like this, right? Okay. This surface, the front surface, is what we shaded in purple here, and the projection of this board, your board is actually shaded in 3D. It's shaded in pink. That's the board, and you project it to the to a vertical panel. It will become a rectangle. It's a rectangle, right? In this way, you converted a curved shape board to a board that we have known before and how to calculate its hydrostatic force before, because in the past 3 lectures we have been derived and calculated how to calculate a board, the rectangle board, how to calculate F, X, CP, and YCP, right? So that's it. That's what does disassemble and projection mean. So disassemble is you figure out what is the force vertically. This is mainly for FV, and projection is mainly for FH. That you convert a irregular or curved, very difficult to calculate surface to a regular that you know already how to calculate, to a board that it's regular and you already know how to calculate the YCG and HCG. I guess it's a little bit tricky to understand, so let's take a look at some problems I prepared. So this is the same as what I taught before. They have it has a different notation, but overall it should be the same. So this is a simple one, and it's a very interesting one. So let's take a look. It asks to find an algebraic formula for the net vertical force F on the submerged semicircular projecting structure CDE. Okay, CDE in this figure. The structure has uniform wave B into the paper. So you need some imagination here. Okay, let me try to draw it. I will try my best to draw it. But this structure actually is like this. If you consider it to be, if you consider it to be, if you consider it to be 3D, it looks like part of the, I don't know, this shape. It seems like a bump here, and that's the surface, and your B is here, right? Its depth into the water or out of the water is your B. And right now it's asking for the vertical force of which is this board, right? CDE here. How can we solve it? So right now, how about I will give you pause the video, take a look how we get a diagram, and then how we disassemble it, because it's asking for vertical force, so projection is not needed here. So how can you disassemble it? Okay. Okay, I hope you work it on yourself and have some idea how to disassemble it. It's even already put a B letter here. That's kind of let you know how to solve it. So let's first take a look at curved plane CD. So it's asking for CDE, right? So let's take a look at CD first. So for CD, how you construct the structure. We said it's from each end of the curved board, a curved surface, to the top of the water, right? So it look like this. And if we take the same notation as shown in this figure, this end is A, and this end is C, and here is D, here is B, right? And theoretically, if we call this weight W1, then the vertical force suffered by the vertical hydrostatic force work on CD is FCD vertical force equals W air plus W1, right? And then let's take a look at DE. I need some space, so let me erase this. Next one, let's take a look at the D. D is here, and E is here, right? And to complete, to structure to get a free body diagram, we need to still make a structure, connect each end to the top of the surface. And still here is A and B. And theoretically, your CD should be here. Right here is C and D. And we have defined previously this section to be W1, right? Then we can say this section to be W2. And the vertical force on DE should equals to W air plus W1 plus W2. Sorry, there are not enough space. Okay. Next, what is the relationship between between FCD vertical and FDE vertical? So this on this figure, it tells you it's FU, right? And it's pointing downward because you can try to think about this curve because it's this curve direction, so the water kind of try to push it down, so this FU should be downward. And for the one FDE, the force that work on DE vertically, and this in this figure is shown as FL. It's shown as FL, right? And F total vertically should equals to FL minus FU. So it equals to W air plus W1 minus W2 minus W air plus W1. Oh, sorry, here should be plus. I don't know why I said minus. And we can see that W air canceled, W1 canceled. And the only thing you have is W2, which means you can consider, okay, here is filled with liquid, and the vertical force is related to the volume and the weight of the liquid you filled here. So what is the shape? A easy way to, I hope you still remember how I draw it. I said, okay, the actual shape of the system should look like this. It's kind of like a board with a bump on it. And the liquid, if here, this section, filled with liquid, how can we calculate? How can we calculate it? We can know the area here, right? And we multiply by B, that's it, right? So what's the area here? We know here the radius is R, so the area is pi r squared over 2, because this is the half of a circle, it's not a full circle. Then V equals A multiplied by B, so it's pi r squared over 2 multiplied by B. And because we're asking for weight here, so we need to know the weight. It equals to rho g V. And if we write it here, it equals to gamma fluid. Depends on what it only tells us the liquid has a specific weight of gamma here, right, in the description. So we just keep gamma, multiply by pi over 2 r squared multiplied by B. That's it. Yeah. A very interesting question. Not difficult, but need some imagination to build a structure in 3D, and need some scratch to check what's going on. Okay, I hope you don't have a lot of questions regarding this one. Next, we're going to talk about this one. This one is super tricky. And I think, so how about you read it by yourself first, and I will put some information here. So for a parabolic shape, okay, and what's actually happened is, if here is B, and then it's X, here is Y, and here is the centroid, and this will be 3/5A. A is here, and the area is defined as A equals to 2AB/3. These are the some conditions you need to know, or some equations that need to be given. This A is the shaded area. Okay, if this area is A. And for this question, it asks for a dam that has a parabolic shape, which means here is parabolic. Let me change the color. It's not readable. Here is parabolic, right? With x0 equals 10 feet, and z0 equals 24 feet. So here is 24 feet, here is 10 feet. The fluid is water. It gives a gamma value, and the atmospheric pressure may be omitted, so which means you don't need to consider about it. Compute the forces FH and FV on the dam and their line of action. The width of the dam is 50 feet. What does the width mean? Width means it means how. Let me draw it. It's, you are seeing this surface, right? And it looks like this inside. Yeah. And yeah, so that means this part as shown is 10 feet, and this is z0 is 24 feet, and then the width width into the water, or out into the paper, or out of the paper, is 50 feet, right? That's it. So first, let's calculate the force vertically. Vertically will be easy, as usual we need to connect one end of it to the top of the surface, and this should be the structure we need to calculate the free body diagram, right? So if you consider about it, it is this shape with a depth in or out of the, let me draw it, with the depth in or out of the system, in or out of the paper, for 50 feet. Okay, so what is the weight here? We said for vertical force, we only care about the weight. So we have our Fv equals rho gv, and this v can be calculated as rho g multiplied by a multiplied by the width of the dam, right? So how to calculate a? It's given here. How to calculate a? We have our a equals 2ab divided by 3, and in our case, that b equals 10 feet, and our a equals z0 equals 24 feet. So our a equals to 2ab/3, which equals, let me add another page. Okay, So it equals 2 multiplied by 10 multiplied by 24 divided by 3, right? And 3, 8. So it equals to 160 square feet, right? I hope it's correct because I do not have it in my note. You can double check, but I think it's correct. Then we have our FV. We plug everything back in, and we know this width is given as 50 feet. And this rho g is given as gamma equals to 62.4 pound force per feet cube per cubic feet, right? So we can plug everything in. We have our FV equals to 62.4, the gamma, multiplied by 160. This is the A we calculate, multiplied by 50. And okay, it's around 500 multiplied by 10 to the 3 pound force. That's the vertical force. How about the horizontal force? For horizontal force, we need to project. Look at this figure, all right? So we need to project the curve to this surface. And what is the area? What the area look like if we project it here? It's here. Let me try to. It's this surface. This is the projection of this surface. Of this surface. Of this curved surface to a vertical panel. It became a rectangle. It's a rectangle board. And what is the area of this board? Based on what's given, we know this line is 50 feet. And we know here is 24 feet. So A can be calculated as A equals 24 multiplied by 50 equals to 1,200. I made an extra 0. 1,200 square feet, right? Where should be the HCG? HCG of this board after projection should be at the center of the board. It should be here. It's at the center of the board, right? So that means HCG equals to let's directly calculate F. F horizontal equals rho G HCG multiplied by A. And HCG is from the centroid to the top. That's 24 feet divided by 2 because it's at the middle, right? So it's 12 feet. So rho G is gamma equals 62.4. And A we just calculated is 1,200. So that make us can calculate FH equals to 62.4 multiplied by 12 multiplied by 1200 and 1200, and the answer what I have is 898,560 pound force. It's quite large, the number. Yeah, but it's comparable with the vertical force that we calculated before. Next, we want to know where the force work at, and that can be converted to calculate XCP and YCP. Don't forget, this is a rectangle board. Then you just you just right now forget everything about a curved board. You just treat it as a rectangle board, right? So we have our YCP equals negative IXX sine theta over HCG multiplied by 8, right? Everything, all parameters is about, all parameters are from the rectangle board. Okay, everything is about a rectangle board. So, and for a rectangle board, your IXX equals to BL to the third divided by 12. Check your, if you check your previous, I think it's the figure we showed previously. Still here is your y. We said it's always pointing topward, so this is your y, and your x should to this direction. Still rotate like 90 degrees C. Let me change the color to get it. Then your b should equals 50. Here should be your b, perpendicular to your y or parallel to your x. I think my x, I should draw it to this direction. Yes, your x should be this direction to make it consistent on the figure. So your b should be 50. Okay, b is 50 feet, and your L is 24 feet. So your IXX equals to 50 multiplied by 24 to the third divided by 12, which is 57,600 square cubic foot. And your sine theta should equals to sine 90 degree. If you look at this board, it's vertical, and we said the theta is the how many degree you rotate by place the board from horizontally to vertically, and this is 90 degree. And that's the reason we have sine theta equals sine 90, which equals 1. And that means our YCP equals negative 57600 multiplied by 1 divided by HCG, we just calculated, it's 24 divided by 2, so it's 12 multiplied by 120. So what you have is negative 4 feet. So that's where the force actually work at, is here. Down 4 feet, you have your CP. Let me change the color. Here should be your CP. And yes, maybe here's already 4 meters. From the center to the down is around 4 meters. And you have your that's work at there. Oh, and at the same time, I forgot to mention, I take it as granted that your IXY equals 0. So your XCP equals 0. And that's the reason I draw it here. It's right below the centroid. Did not go anywhere else, just on the line here, and then 4 feet below. So, and at the same time, the combination of this force is F, it works there, and the actual combined force is FH squared plus FV squared. That equals 1028 multiplied by 10 to the third pound force. Yeah. The last thing I want to do is, I think it reads okay on this figure. So I want to try to remind you one more time. Here is the centroid. Yeah. After you project it, you just treat it as a board, like a regular board, rectangle board. You don't need to think about it's a curved board anymore. And here is the centroid, and below it is the what from YCP you can calculate the equivalent location or center of pressure where it is, which is shown as green. That's 4 feet below. Then through this calculation, we know, okay, where is the equivalent force and what is the magnitude of the equivalent force. And that's it. Oh, yes, I actually have it here. I forget. This is the equation to calculate IXX and IXY based on B and L given. You can refer to this one to understand what is your B and your L here. Okay, that's the end of this lecture. This lecture, we talk about hydrostatic force. We said we need to first disassemble it to calculate F vertical force first, and then we need to do a projection to simplify it to a calculable regular board. That's the 2-step, and we calculate FH and FV individually. That's it. Enjoy.